Welcome back, everyone. In this lecture we are going to talk about construction dewatering. Specifically, we're going to talk about how we use some of the analytical solutions we found to design systems to dewater excavations. And this is a fairly common engineering and construction practice for regions with high water tables. So one of the ways that you can dewater an excavation where you happen to have a high water table is to use what is called a well point system. This is typically used where you have fairly shallow water table and you have a series of pipes that you inject into the ground. They're called well points, and they have a screen on the bottom. And they come up to the top, and they're all connected to a single pipe. And that pipe is connected to a pump, and that pulls the water out. And then together, these create a cone of depression, which, so this is the water table, and it goes down below the base of the excavation and keeps it dry. Presumably, you construct a foundation or a waterproof basement in there, and then you can let the water come back. In a lot of regions where you have high water table, traditionally it was customary that you create a concrete floor and concrete walls, and you could even put a tar or other things on it to try to waterproof it. But if you do get a leak, often they'll put in some kind of sump and pump that out. Another thing that's becoming really common these days is there's an additive that you can put in the concrete, such that when the concrete cracks and it fills with water, that additive swells and it seals itself. So it makes for extremely waterproof foundations. And there's a hydroelectric plant up the mouth of Provo Canyon here near Provo, Utah, and they have a high water table. It's right next to the Provo River, and they have a very deep basement where the hydroelectric plant, where the pipes come down and the turbines rest, and they've used that kind of concrete, and it's kept it really dry. It works really well, so that's kind of a fun way to keep things, or an effective way to keep things dry once you've built your system. Now, how do you put all those well points in the ground? They have a jetting system that works really well. So basically, you connect high pressure water to a jet that comes out the end, and then you can basically just push it in the ground. This actually works pretty well. When I was a kid, we used to take a hose and do this, and if you stick it in the ground, you can it's amazing how deep you can push it, because that jet reduces the pore pressure in the soil and makes it soft, and it's a really cheap and effective way so you basically push these in the ground instead of drilling holes for them, and it can work really well. In other cases, you might use a deep well system where you get a drill rig out and drill a hole, and then put a deeper well screen in there. And again, and in this case, you can see each of these wells has its own electric turbine that pumps it out and is pumping it into a pipe collection system, and then taking it over and doing something with it. In this case, they're discharging it into some nearby water system. And so there's some interesting designs you can come up with here. One area where dewatering is really critical is for mines. Almost every mine has to have a dewatering system in place. And so if you get really good at dewatering, you could probably make a career working in the mining industry. And they use the same kind of systems, a combination of drains and wells, and they move sometimes massive amounts of water to keep the mine dry. Not just an open pit mine, but when you have tunnels and boring into the ground, they have to dewater that as well. So when you're designing a dewatering system, you need to know how much water are we going to have to pump out. How many wells should we use? What is an optimal number of wells? You want to make these economical. You don't want to waste money. Where do you locate the wells? Should you use, instead of wells, should you use a French drain or a trench? And we can do this in a lot of cases with analytical solutions, with the well equations that we've derived, or with the Dupuy rectangular soil equation that we used. You can also use, if things get complicated, you can use a numerical model such as ModFlow, and you can handle, with that you can handle just about any kind of boundary condition, or you can have multiple soil types and anisotropy and all kinds of problems. But we're going to mainly focus on simpler solutions here. So what if you have a dewatering trench? Sometimes we surround our site with a trench and a permeable trench, and then you pump water out of the trench, and then you can then do an excavation on the other side. So you have a source of water somewhere, and then the trench is used to keep it dry. Well, if you can estimate the hydraulic conductivity, what your initial water table height is, and what it needs to be inside the trench, then you can use this equation to calculate how much water you're going to have to pump per linear foot of the trench. So what kind of trenches are we talking about? Again, it has to be a permeable trench. Here are some examples. These are sometimes called French drains, where you make an excavation, put a pipe in the bottom, and then backfill it with sand or gravel. You'll notice in this one, they've lined the sides of the trench with a fabric before they put the gravel in. If you have clay soil and you fill it with a trench with gravel, that clay can then work its way into the gravel and basically make it impermeable, so that fabric will keep the fine particles from coming in. And this one on the right has actually two pipes in it. These are fairly common. Another one that is really interesting is a biopolymer slurry trench. You start to see these more and more. The way you dig a slurry trench is you have this track hoe with a really long arm, and you fill the way a slurry trench works is when you dig a trench, you're worried about the sides collapsing. But if you fill that trench with a slurry, the pressure that water forms on the side of the trench can keep it from collapsing when it otherwise would. And this is a common technique for building an impermeable barrier. Sometimes we want to contain a system. For example, if we're doing a dewatering system, we may do an analysis with our wells and find out that there's a massive amount of water we have to pump. So you can surround the site with a slurry trench cutoff wall, in which case, you dig one of these trenches, and then in that slurry you mix typically something like bentonite, which makes a highly impermeable slurry, and then you push the soil back in, and you effectively have a low permeability clay wall that surrounds your site. In some cases, they'll even put high-density polyethylene in interlocking sheets down inside this trench, but typically it's just some low, they backfill it with the low permeability clay. But so that's a way you create an impermeable trench. What if you want to make a trench that is permeable? Well, in this case, instead of adding bentonite to the slurry, they use a guar gum or a xanthan gum. That slurry has to have some viscosity to it that puts, otherwise the water just seeps into the soil. And the gum it forms a cake on the sides of the trench and allows that water pressure to help keep that open. Well, so you use that gum-based drilling fluid, then you put a pipe at the bottom, and then you can backfill it with gravel, and the gravel just goes in with the gum. But then that gum biodegrades after a few weeks, and you're left with a French drain. And why not just, why bother with the slurry? Well, the slurry allows you to build a deeper trench than you could otherwise in order to build a really deep trench, you either have to be in a really strong kind of soil, or you have to have braces to hold up the side of the trench, which can get really expensive. So this is kind of an economical way to build a large permeable barrier or trench. Okay. What if you want to use wells to do your dewatering? Either a well point system or a set of deep wells. And we're typically working in unconfined soils. So if we go back to our, our unconfined, well equations, and then we apply the principle of superposition that we talked about in our previous lecture, we can then experiment numerically and create a series of wells around our trench, and then at any point inside the domain of the trench you can calculate what the head would be with all of these wells pumping. And you check all of the locations in your excavation. I said trench before I meant excavation. So you have some excavation in here inside of the wells. And this will tell you the height of the water table after pumping as a result of the combined drawdown effect of each of these wells. And if that head is below the bottom of your trench, you've effectively dewatered it. So using these equations, you can experiment with different pumping rates and well designs. You can change the number of wells, the location of the wells, and you can do this like in a spreadsheet or in a Python code. I have a Python solution which we'll go through in class, and it works really well. It's really powerful. Now, you have to be careful here. One caveat is that the derivation of the unconfined aquifer relies on the Dupuy assumption. The exit point coincides with the tailwater. This is a little unconservative. As the water table gets closer to the bottom of the aquifer, this error gets greater. So the closer you get to being right here at the bottom, the bigger that difference is. So you might want to be careful using this method if the aquifer is close to being dewatered. You could either build in a big factor of safety or use a numerical model instead.